All right. So turn in the homework here if you haven't. So ready to begin? So if I remember right, where we left it, we were thinking about Bob and Anna, who were separated at birth. And Anna was sequestered away in this fast-moving spaceship. And she went out to the star, 40 light years away. And when she came back, we had a big family fight, okay? Because Bob said that he aged 100 years in this process, and we worked through how. And Bob said that Anna aged 60 years. Anna agreed that she aged 60 years, but when she gets back, she says Bob is 36 years old. Bob says he's 100 years old. And I said the reason this happened is because Anna was actually in a non-relativistic, in an accelerating frame, general relativistic effects, which are not just some little detail. They completely dominate what happened. And that's the reason. Now, you might think, well, that's kind of a cop-out. It's not a cop-out, but I don't know. So let me see. So Bob and Anna are fighting about this, and they get cousin Carl to come in. So we're going to bring cousin Carl in. He comes riding in at 0.8 C, heading the same way as Anna was heading. And, okay, so maybe we can get around this, this business where I said hocus pocus, general relativity, no problem. So Carl's going to go right past the star, right when Anna's there. He'll be the return trip. And he's in his own frame, and I'm not going to have him accelerate or decelerate. He's just going along at 0.8 C. So there's no general relativity that you can hide behind, all right? This is a perfectly reasonable setup with no one in a frame that isn't just steady. No one in a non-inertial frame. Well, what to say about what happens? Well, one thing we could say is, look, Carl eventually gets to Bob, and he asks Bob, how old are you? And Bob says, I'm 100. Okay. So when Carl reaches Bob, Bob is 100. And okay, I'm not going to pretend. Anna's answer is wrong, because there are general relativistic effects. So when Carl shows up, Bob really is 100, okay? That's the right answer. Bob just sat there. Of course he's still 100. I mean, we have special relativity. It's really weird. But we can't possibly concoct some scheme where if I age 100 years, I'm not 100 years old, right? So Bob's 100. Carl shows up. Bob says I'm 100. Now, if you remember how we derived this, we considered Anna going across the distance she saw, which was contracted, the time it took her given her speed, and then the fact that she thought Bob had even less time than that because Bob was in a frame that was moving with respect to her. Bob ended up aging, actually 36 was the total for the two, but 18 was how much he aged during one of the legs, okay? And so Carl comes along at 0.8 C. That's exactly the argument that applies. Carl thinks that Bob ages 18 years in the time it takes Carl to go from here to here, okay? The same as what Anna would have seen if she jumped frames. So Carl says when he is at star with Anna, Bob is 100 minus 18, which is 82 years old. Okay? But Anna says, Bob is 18 years old. Because Anna just left, and I just argued that that's how she came, she did her analysis, and she said he's 18. She said it was 18 when I came out, and I went back 18 years each time for Bob. So this is the same actual disagreement, similar disagreement to the one here when Anna arrives back at Bob. Is there anything they can agree on? I mean, this is starting to look like a Jerry Springer show, right? Well, yeah. Let's think about, and I think this is a worthwhile analysis, let's think about Anna and Carl looking back at Bob, okay? Yeah?
We're just saying Carl was starting from the start.
No. I mean, he's a cousin. I don't know how they did this family. He's a cousin. He's been way off at, minus infinity, and he's coming by, and he was, I don't want to make him accelerate or decelerate, so he was just whizzing by in the other direction. Happened to be passing by. Thought he'd drop in. So I want to hang on to this notion that was so instructive before to look at some coincident event. So let's imagine that Bob had a birthday and sent out a snapshot. In the modern days, we can say he took a digital photo and then he used a wireless transmission, transmitted the photo. Okay, so here's the JPEG racing along at the speed of light. And let's say it arrives at the star when Anna arrives at the star, when Carl arrives at the star. And they all get to look at the JPEG. Okay, that ought to be rational. So let's look at it from 3 points of view. So we're gonna look at the JPEG. So what does Bob see? Well, Bob says something simple. He says, it's going to take 40 years for the JPEG to get there. Okay. Yeah, I'm saying something very simple here. He needed the JPEG to arrive when Anna arrived. Anna was going 0.8c. If you remember, that said that Anna took 50 years to get there from Bob's point of view. That's very simple. That's 40 years divided by 0.8. Okay? That's half of the 100 years. Okay? Very simple. So the light needs to get there in 50 years. It's going to take 40 years because it's going at the speed of light. So when does he send the JPEG? On his 10th birthday. So Bob says the photo is of 10th D-Day. That's what Bob says. What does Carl say? Same sort of reasoning. Carl sees some distance that the light traveled, and he sees some velocity that the light went. Okay? Now, Carl sees and this is a little bit, you have to be a little bit careful. Carl sees the light going at c, but that's not the situation he sees. In Carl's frame, let's pretend we're in Carl's rocket ship and just sitting there. What does he see happening? He sees the star and Bob racing at him because Carl's running along, right? So he sees them coming at him. And then he sees the light trying to catch the star, okay? So he sees a relative velocity between the star and the light, okay? So he sees the star. He sees the light coming at him with at the speed c. I said everyone sees c, but he also sees this star moving away. So he sees the light moving with respect to the star at a different speed. All right. So here's what Carl says. Carl says that the distance. Well, he sees the He sees the time for the JPEG is the distance it goes divided by the relative speed. So now the distance it goes is not 40 light years. Again, Earth and the star are both racing past him. He sees a contracted distance. So he sees 40 light years over gamma. Okay? And then from his perspective, the star is moving at 0.8 c, and the light is catching up, moving at c. So the relative speed of the two is the light is overtaking the star at 0.2 c. I think that was my off. Okay? And gamma was 5/3. So this is 3/5 times 40. And dividing by 0.2 is to multiply by 5. So that's 3 times 40. It's 120 years. Okay? So Carl says that the light took 120 years to get there. However, Carl also sees Bob as racing by. So Carl sees Bob as having less time having passed. So Carl says delta T Bob is delta T JPEG divided by gamma, because it's less time has passed for Bob during the 120 years in his frame that he thinks it took, or that it did take in his frame for the light to go. Okay? So that's 3/5 of 120 years, which is 72. Okay? If you do the math. But from working backwards, when Bob catches up, when Carl meets Bob, Bob is 100. Carl thought that it would take 18 years of Bob's time to get there. So Bob thinks Carl is 82 years old right now. And he thinks that 72 years has passed while the birthday signal was sent. Therefore, Carl says the birthday is 82 years minus 72 years equals 10 years, the 10th birthday. Now that is a fair amount to think through. But I get the same answer. I get the same answer that Bob and Carl agree. But clearly that may have been a tad much to think through, but that's, it's all there. Carl sees the light moving. It goes a contracted distance, a certain relative velocity. I take that into account. That's a time, but that's the time in Bob's frame. In Carl's frame, slower time in Bob's frame. That's how I get the 72 years passed, but he thinks Bob is 82 at the time, therefore it had to have been his 10th birthday. Finally, let's do Anna. Again, it's the same sort of analysis as here. Anna says the time for the JPEG was the distance divided by the relative speed of the JPEG and the star. The distance is the same contracted distance. She sees the star and the Earth. She's racing past. So that's 40 over gamma. But what does she see as a relative speed? Right, so Anna's racing along. Well, Anna's racing along, but if we take her to be at rest, then the star and Bob are racing along at 0.8 c. While Anna always sees the light going at c. So she sees the light and the star approaching at 1.8 c. So divided by 1.8 c. Okay, and this is light years. All right, so that's, again, this is 5/3, so that's 3/5 times 40. And I'm dividing by 18. I'm dividing by 1.8, which is the same as 18 over 10, which is the same as 9 over 5. And so that's to multiply this by 5/9. The 5 cancels. So it's 40/3, okay? 40/3 years, okay? That's the time for the JPEG, but also Anna thinks Bob's clock runs slow because Anna see, yeah?
How would you know the speed over 1 c? Would do 1.8. I understand it could be additive from Galilean, but it can never be above 1 speed, right?
Hold that thought. I mean, what can't happen is that you and I actually see a speed of each other greater than c. However, if you're running at greater than ½ c this way, and I watch you, and I watch someone else run at greater than ½ c that way, no contradiction there. You guys approach each other, as far as I'm concerned, greater than c. And that is indeed what Anna's doing. Anna is cruising along. She's racing at the star. She considers herself to be at rest. The star is racing at her. The remarkable thing about the relativity, the Michelson-Morley result, is that that light that left from Bob, in her frame, is still going at c. Okay, so she sees it going at c. She sees this other thing coming at her at 0.8 c. The sum is 1.8 c. Okay, no problem there. It's not violating. You can't have two things relative to each other actually think they're going faster than the speed of light. Okay, so that was delta t JPEG. And just as for Bob, just as for Carl, delta t of Bob is delta t JPEG over gamma, which is 40/3 times 3/5. Which is 8 years. However, Anna thinks, or not Anna thinks, in Anna's frame, Bob only aged 18 years. And she thinks for Bob's time, it was 8 years of transit time for the light. So she also agrees. 10th birthday equals 18 minus 8. This 18 years minus that 8 years. Okay? This is all in the textbook. Okay? But I thought it was worth just going through it. So it all holds together. It all holds together. And these frames just have a different view of things. I mean, there's several things here that just stand out in contradiction. Anna said that Bob aged 18 years while the light was transmitted. Carl said that Bob aged 72 years while the light was transmitted. They just have a different view of things because they're in different frames. If you wanted to make something like time travel, maybe this, you look at this and you say, oh, let's get rich in the stock market. Because somehow for Carl, Bob's really old, while for Anna, Bob's really young. And so you might think Carl can find out something about what Bob did and tell Anna, and she can go back and make some money. Okay? But if you think that through, that can't work. The reason they can't work is that Carl would basically have to know about, although for Carl's going to view Bob sort of in the future, like when he shows up, Bob is much older. When they're at this point in time, all they can really learn about what happened since Anna left Carl when he was born is whatever they see here. And even though there's this confusing story where they think very different amounts of time have passed or whatever, the point of showing that they all agree that it's the 10th birthday signal was to show that at least, again, if you come to just a simultaneous event, what they can see at this point in time, there is no contradiction. They all just saw Bob's 10th birthday, the photo transmitted. That's what Bob thinks, that's what Anna thinks, that's what Carl thinks, okay? And so there's no transmission of information. If Anna wanted to hop onto Carl's ship, or Carl wanted to hop on Anna's ship and change everything, then we're right back to what I said last time. That changing of frames, the hop from one ship to the other, is to instantaneously decelerate and then instantaneously accelerate, let alone that the forces would just instantly vaporize either one of them that tried it. There would be these huge general relativistic effects which would completely alter their time frame. And that's the apparent contradiction in these times. You guys really seem floored by it, or just down. So you get, is that, okay? Thinking this through, I think, is useful. It's not exactly the same as working most of the problems. But if, I think there's useful, useful exercise to think that through. Okay. So let's do something now. Let's kind of go to the next step. We've examined this to death, and in your homework you examined, the effect of the two frames. So let's just take the next step. We found out now with this in this craziness with the speed of light being the same for everybody, that our notion of space and our notion of time have changed, and they're not the same for different frames. And let me write down the Lorentz transformations once again. X prime equals gamma x minus vt, and t prime equals gamma minus v over c squared x plus t. And just as a reminder, talking about a prime frame and an unprime frame, with this frame moving at the x direction with v. So, okay, let's think about velocities. So the simplest thing is the velocity of the two frames relative to each other. We've already talked about that. I've argued that it just doesn't make any sense to think that, sorry, too many negatives. It's very straightforward. They both agree on v, right? If I move past you guys with one velocity, we both agree on what that velocity is. What gets interesting is if we consider an object here that's moving and has some velocity u in the unprime frame, okay? Thinking about this for a second highlights what I mean in terms of notation here. If there's some object on the x-axis with a specific value of x, I'll just call it x, right? That's its value on the x prime axis in the other frame. So to think about velocities, we'll take differentials. dx prime is gamma dx minus v dt. And take a differential of the time equation, the time Lorentz transformation. Note I'm saying v is constant. I'm not going to have accelerating frames, or then I have to take differentials of the v as well. And let's just divide the two. dx prime dt prime equals, divide this by that, the gamma drops out, dx minus v dt over minus v over c squared dx. That's a plus. Plus dt. Divide both of these pieces by dt. And so now clearly some notation, dx dt is nothing other than the velocity of this object in this frame. And dx prime, dt prime, is nothing other than the velocity of this object in the prime frame. So this is u prime. And I'm going to call it u. U will always now refer to velocities of objects moving in the frames, whereas v is going to be the velocity of the one frame with respect to the other. Is u minus v over 1 minus v I botched that little bit about algebra. If I divide this thing by dt, I meant to write dx divided by dt there, plus 1. Apologies. Okay. Let me rewrite that. And really, actually, it's useful now. I need to distinguish motion in the 3 dimensions. So I'm gonna put a tag on u to say that it's the x velocity, because there's also going to be a velocity in y and a velocity in z. So ux prime equals ux minus v over 1 minus v times u over c squared. I mentioned it once or twice, but didn't really stress it. In this basic Lorentz transformation, z prime is z and y prime is and y prime is y. Remember how we argued in the very first day that we did this? We argued about that we did the time dilation watching a light beam pass up and down in Anna's frame relative to Bob's. And then we got length contraction by having them measure Anna's spaceship as it passed. If Anna wanted to measure some vertical height, she can do that at one place in her spaceship, and Bob can do it at some moment when they all are coincident. And then there won't be any of this funniness about the time difference between the front and the back of the ship in anyone's frame. So so if you're measuring in a perpendicular direction to the motion, okay, you can just do that measurement and they'll both agree on the measurement. So y and z simply don't change. If you don't like that complicated explanation, pretend I never said it, right? It just kind of stands to reason. If we're moving along the x direction, the y direction, the z direction, they're not affected. Okay, so just y prime is y, z prime is z. So if you look at this derivation, right, dy prime is dy, and dz prime is dz, and therefore uy prime, which is dy prime, divided by t prime, is going to be dy over, but still the dt, the denominator, has all this junk, minus v over c squared dx minus plus dt, okay, and divide by dt everywhere, and this is uy prime over gamma times 1 minus v ux over c squared. So that's how the velocity in the z in the y direction transforms, no prime there, and this is how the velocity in the z direction transforms. These aren't sort of nice, clean equations. Well, if you consider the Lorentz transformations nice and clean, which after you get used to them for a while, maybe you do. They're a little uglier, but this is reality. This is what happens to velocities. Okay? So now we can ask the question, I think it was you asked, about things approaching near the speed of light. But again, I don't want to belabor it too much, but let me just reiterate on this point about just a moment ago. I did do velocities when I did this whole argument about Anna and Carl and Bob, but I didn't use any of this. What I said in the one case was that Anna's moving along. She's moving, but in her frame, she just thinks Bob's moving, and she thinks the star's moving. But she also sees sorry, Anna was going that way. So she's going that way. She sees these guys going this way. I was doing Carl, not Anna. Okay, sorry. Anna's moving this way, or if I consider her to be at rest, she sees Bob moving backwards. She sees the star moving backwards. She sees the light moving at C. That's not what I drew. I didn't ask, does one of these people, or people, Anna in this frame, Bob in that frame, do they see two different objects? I said, do Anna and Bob in different frames see the same object? All right? So fair enough. Let's apply this new reasoning to this situation. But what would I be asking? The question I might ask instead, let's go back to leaving Bob at rest. Let's ask a very basic question. So Anna's moving at 0.8 C. So that's S prime. V, 0.8 C. Bob's here at rest in S. And there's the photon. There's the JPEG. There's the JPEG of his birthday. And it's got UX equals C. Okay? Let's apply the formula. UX prime is UX minus V. This is UX, which is C, minus V. V is 0.8 C. I'm not even going to plug in the numbers. You'll see why in a second. 1 minus V times U sub X. It's always U sub X here. C minus V times 1 over 1 minus V times U sub X is C over C squared. Okay. So that's C minus V over 1 minus V over C, because that cancels. Let's multiply top and bottom by C. Okay. The bottom, this becomes C minus V. The bottom is simply C minus V. And that C is still sitting there. These cancel, and that's C. I didn't have to plug in the value of V. That is what I wanted. That's how we started the whole darn thing. I said here at Case, Michelson and Morley proved that the speed of light is the same for everyone. I said, let's start thinking about what would be implied by that. I worked out some rules. I worked out the Lorentz transformations. I've derived how one frame versus another frame sees velocities. I applied it to a light packet, and very nicely, I got the answer I needed. UX prime is C, and UX is C. And it just falls out of this kind of icky equation. Okay? So that's good. That's really great. All right, so that's really all I'm going to say about velocity transformations directly. Relatively straightforward to have derived this. Equation's a tad messy, but I get this really great result, which is that the speed of light does what it's supposed to. So I have the Lorentz transformation. I have this basic setup. Let me just write down the reference that I just derived. Okay. So now what's going to happen to mechanics? F equals ma and whatnot. Because clearly things have changed quite a bit. X is not simple anymore. T is not simple anymore. V is not simple anymore. You know, aren't I going to be in trouble with mechanics? So let me first make just a couple of comments. And you can relax. Actually, to do mechanics fully in relativity is a lot messier. We're just going to scratch the surface. We're going to get the big results, but we're not going to work lots of messy problems, okay? We're not going to shoot a projectile relativistically and watch it do all its stuff and rework out all those equations, right? Not going to put you through that. But we're going to pick off the low-hanging fruit. Now, if you say mechanics, right, first thing that should pop in your mind is F equals ma. Turns out that often ma is also known as m times dv dt, right? Which, if mass isn't changing, is d by dt of momentum, is p dot, okay? Momentum, in many respects, is a more fundamental quantity than mass and acceleration. In fact, just as a preview for what you'll learn in a very much upper division mechanics class, if you assume there's this beautiful theorem, actually it's mathematically worked out by, I forget her first name, but a famous mathematician, I think Emily Noether, Noether's theorem, that if you work out the mechanics of a system, you fully develop a theory of mechanics, and you say that that mechanics is the same at various places in space, automatically embedded in the mechanics is the fact that momentum is conserved. And so in many respects, momentum conservation is an absolutely fundamental feature of the physical, it's both a feature of the physical world, and it's sort of at a theoretical level, sort of at a higher plane or elevation than F equals ma. The notion that you should deal with momentum should be conserved. There's a similar result from Noether's theorem, which is that if your mechanics doesn't change with time, energy is conserved. Okay, and so in a few years, you'll see how that works out mathematically. All of that is to say, I'm going to punt and not look at A, I'm going to look at P, okay? And I gave you some look at the future, sort of fancy stuff to justify that. And what's the most simple, one of the more simple things about momentum is momentum conservation. Okay, so let's remind ourselves what I mean by momentum conservation. Let's take a fairly simple setup. Let's take a fairly simple setup. So I want to look at momentum conservation. Suppose I have a mass 2m striking a mass m. And let's say that this has a velocity, and I'm going to still use this notion of u, this notation of u for the velocity. I'm not going to distinguish x and y for a while, just everything's in x. But I'm going to call it u initial, and that's a half c, okay? And that's the before, if you will, or the initial situation. In the final situation, let's say they stick together, and then there's a u final, right? Very simple. Now, ordinarily, if you have a collision like this, you might have energy conservation, you have momentum conservation, and you might have an energy condition. There's no energy condition here. Why? Because I made them stick together, and that's an energy non-conserving. I mean, overall energy is conserved, but I converted, kinetic energy into heat by mushing them together. So I don't have an energy condition. And so this is final. And so we have a very simple thing that P initial, this is moving, that's not, it's 2m, it's m times v, or m times u, it's 2m times ui, so it's 2m times 1/2 c, it's mc. Okay? Very straightforward. And P final is 3m u final. And momentum conservation is to say that that's equal to P initial, to say that it's equal to mc, and therefore 3m u final equals mc. M cancels out, and u final is 1/3 c. Okay? Which happens to be equal to 2/3 u initial. If I'd left it all symbolically, that's what it is. Straightforward, right? So that was just a reminder, that's what I mean. And, you know, so the more formal way to talk about it is I say there's a total momentum for the problem. In general, I should write down that that's a vector, but I'll skip that. It's implied. And that means I take all the particles and I sum them, and that's conserved. Right? It's conserved if there's no external forces. Okay? All right? Now, I don't think you've ever done this, but there's the basic, now in relativity, we've talked about changing frames. So I don't think you've ever done this, but let's look at this from a different frame and see if it still all holds together. Okay? So let's jump to the S prime frame. Right? Let's do something really simple. Let's look at a frame that's moving at 1/2 c that way, okay? So that this guy will be at rest and that guy will be moving. All right? So V is minus 1/2 c. We're going to have an S prime frame, this time for the first time moving backwards, or moving towards negative x. That's fine. All right? And let's forget relativity for the moment. Mass 2m is at rest. Mass m in this frame has ui prime equals minus 1/2 c. So that's initial. And the final, well, instead of working it out, no, let me work it out. Sorry, let me work it out. So let me apply momentum conservation. Sorry. Let's just see if momentum conservation holds, and if I do just normal velocity transformation. This is all Galilean velocity transformation. So in other words, I know that ui at the end was 1/3 c. Standard old, it's called Galilean, because actually Galileo did talk about this in a book of all things. He talked about velocity transformations, is that u final prime is nothing more than the relative velocity. So we're moving backwards with minus 1/2 c, and this is 1/3 c. Galilean is just this part in the numerator here. You take the prime frame, sees the normal velocity minus v, and there's just a question about the signs here. When v is defined that way, then you subtract it. And so u final is 1/3 minus v, which is minus 1/2. Minus 1/2, both of these times c. Now I've done a really bad job here managing space. 3m there. U final was 1/3 c. U final prime is 1/3 minus 1/2. It's 1/3 and 1/2. embarrassing. Yeah, I said something silly here. Do you guys see what I said? Speak up, please. I want this to move so that this is moving and that's at rest. Obviously, I didn't mean that. I meant this. I was being very, very silly. I apologize. Right? If this guy's moving at half c and I want him to be at rest, then I just go the same speed he was going. So that's still fine. UI initial is minus a half c because it was 0 minus v. There's no negative sign there. There's one negative sign, not two. And so this is minus, it's 1/3 minus a half, it's minus the 6c. All right? And so let's examine momentum conservation. P initial prime is m times minus 1/2 c minus 1/2 mc. P final prime is 3m times minus 1/6 c, which is minus 1/2 c. Okay, minus 1/2 mc. So sorry I got tripped up in the algebra, in the setup a second. I'm saying something simple here though. I'm saying that in the first frame, momentum was conserved in a very simple way. I take another frame that's moving in with respect to the frame, and momentum was conserved in a very simple way. Okay? However, if I use relativity to do this transformation, I now know that this isn't correct. U initial prime for these guys has to be examined. And it's going to be U initial minus V over 1 minus U initial V over C squared. And I have to apply it to all three of the I'll apply it to all three. Now for the 2m mass, it was moving at U initial equals 1/2 c, okay? And now I'm going to move at 1/2 c. And in the numerator, then I just have 1/2 c minus 1/2 c. That makes sense, right? That can't change. The numerator just, it still just turns into 0. But the denominator, but when I look at, okay, so that's this guy. When I look at this guy, so 2m is still at 0. U prime equals 0. M, I have U initial prime equals, U is 0 minus 1/2 c. And the numerator is this 1 minus U times V over C squared. Well, U initial again is 0. So it's 1 minus 0. So this is also just minus 1/2 c. The same as it would be without relativity. But U final prime, okay, that's this 3m that in the unprimed system has a velocity of 1/3 c. I apply the transformation equation. I have 1/3 c minus 1/2 c over 1 minus 1/3 times 1/2, both times c squared over c squared. C cancels out. The third minus 1/2 is again a sixth. So I have minus 1/6 c. This is 1 over 1 minus a sixth. That's 6/6 minus 1/6 is 5/6. In the numerator, the 6's cancel. It's minus 1/5 c. Okay? So with relativity, P initial prime, it actually hasn't changed because the thing was at rest and the transformation is the same. Minus 1/2 mc. But P final prime is 3m times this thing. It's minus 3/5 mc. So momentum conservation has failed on us. It has just failed on us. It wasn't normal momentum conservation. It wasn't just simply I say, oh, momentum conservation. Much more carefully, I said, if momentum is conserved in one frame, is it conserved in another frame? And I see that it doesn't work. Physics is going to have to be the same in these frames. They're going to, it's going to have to all work out. So basically, I said the momentum is the important thing to look at, and I've seen that so far it's not working out. So the answer is, and this will be about, elaborated on Monday. And by the way, Pete Kiernan, who does the recitations, is going to lecture for me on Monday. I have travel I have to do. P equals mv is no longer true. Okay? That's got to be modified in relativity, and that'll be the topic for Monday. All right? Have a nice weekend.